Vector A has a magnitude of 15 and an angle of 122 degrees. Vector B has a magnitude of 23 and an angle of 46 degrees. What is the magnitude and angle of the resultant vector of A plus B? Let's read through this again and find the important information. We're given two vectors. Vector A has a magnitude of 15, but we're not given any units. It has an angle of 122 degrees. So let's write down A equals 15 and theta A is 122 degrees. Vector B has a magnitude of 23 and an angle of 46 degrees, and we'll write that down. The problem is asking us to add vectors A and B and find the magnitude and angle of the resultant vector. Let's call the resultant vector C so it's easier to keep track of, and write down that we're trying to find C and its angle, theta C. Next, let's draw these vectors to get an idea of what we're trying to find. The problem didn't give us any length units, and we're told vector A has an angle greater than 90 degrees. That should tell us that these angles are probably measured counterclockwise from the positive x-axis, which is the conventional way to describe angles using a single value. So let's draw vectors A and B starting at the origin of the x and y axes. Vector A has an angle of 122 degrees from the positive x-axis, and we'll label the magnitude as 15. Vector B has an angle of 46 degrees and a magnitude of 23. Remember, unless you use some tools, the angle and lengths of these vectors won't be accurate. So these pictures just help us see the vectors and which directions they're pointing. Now, let's use the tip-to-tail method to draw their resultant vector C. First, we draw A, and then we start B at the end of A. Then we draw vector C from the start of A to the end of B. If we want, now we can draw vector C at the origin to get an idea of its direction. However, if we didn't draw vectors A and B accurately, then C won't be accurate either. So we probably don't want to rely on this picture to determine its direction, and you can skip this if you want. But seeing vectors A and B added together visually is probably helpful. Okay, so what are the steps for adding two vectors? And what equations could we use to solve this? We learned that if we're adding vectors, we can find their individual components and then add those together to find the components of the resultant vector. Then we can use those to find its magnitude and angle. So if vector C equals vector A plus vector B, then the component Cx equals Ax plus Bx, and Cy equals Ay plus By. We know vectors A and B. We can find their components, then find Cx and Cy, and then use those to find vector C. We do need some other equations to work with vectors, like the trig functions, but these here will remind us of how to solve the problem. So first, let's find the components of vector A. Let's start by using the 122 degree angle that we're given. We learned that the x component, Ax, is equal to the magnitude, A, times the cosine of theta. We plug in 15 for A and 122 degrees for theta, and we get negative 7.95. Notice that the x component is negative because it points in the negative x direction, and plugging in this conventional angle takes care of the sign for us. Next, Ay equals A times the sine of theta. We plug in the same values for A and theta, and we get 12.72. Let's save these components at the top. Another way we could have found the components is by using the reference angle. 180 degrees minus 122 degrees is 58 degrees, which is the angle between the vector and the x-axis. And if we draw out the components, it's the angle inside the triangle between the vector and the x component. If we plug in 58 degrees, then AY is still positive 12.72. But now AX is positive 7.95. That's just the length of the bottom side of this triangle. But like we said, AX points in the negative x direction. And since we're adding vectors, we need to include that negative sign for things to work out. Now let's find the components of vector b. Just like with vector a, bx equals b times the cosine of theta, and by equals b times the sine of theta. Now we plug in 23 for b and 46 degrees for theta, and we find that bx is 15.98 and by is 16.54. Let's also write those at the top. Now we can add the x components and the y components to find the components of vector c. Cx equals ax plus bx, which is negative 7.95 plus 15.98, which gives us 8.03. Notice that we're always adding the two components, but we can plug in negative values. Next, cy equals ay plus by, which is 12.72 plus 16.54, which gives us 29.26. Now that we have the components of vector c, we can find its magnitude and angle. We use the Pythagorean theorem to find the magnitude. If we rearrange that, then c equals the square root of cx squared plus cy squared. We plug in 8.03 for cx and 29.26 for cy, and we get 30.3 for the magnitude of vector c. To find the angle, we use the inverse tangent function, where theta is equal to the inverse tangent of the y component over the x component. When we plug in the values of cy and cx, we get 74.7 degrees for the angle theta. The angle we found is the reference angle between vector c and its x component, which is how the tangent function works. cy is the opposite side and cx is the adjacent side to this angle. But if the problem is asking us for a single value for the angle of vector c, we probably want to find its angle counterclockwise from the positive x-axis. So is that this angle or a different one? If we drew the vectors accurately, we would see the vector points in the positive x and positive y directions. But we don't need the picture to tell us that because cx and cy are both positive. So if this is the direction of vector c, then 74.7 degrees is the angle relative to the positive x-axis. If cx was negative, then the vector would point to the left, and we'd have to find 180 degrees minus the 74.7 degrees to find the conventional angle. So that's how we would solve this type of problem, which involves adding two vectors and using conventional angles relative to the positive x-axis. We had to really keep track of our angles and our positive and negative signs, but as we'll see, some vector problems are a lot simpler.